If I can't picture it, I can't understand it. Albert Einstein. Dear students, today in this lecture we discuss about dynamics of a system of particles and introduce a very beautiful concept, center of mass, or sometimes it is called mass center. Before we proceed, how to determine mass center of a system of particles or how to use the idea, let us discuss a very interesting experiment. Here in this diagram, you can show a rod. Actually, this is a snapshot taken after regular intervals of a rod thrown in such a way that it rotates in the motion. You can throw a rod like that. Just take a rod, hold it from one of its ends and throw it. So it will follow such kind of motion. Now if you think any particle of the rod, it will move something very complex motion. But again, here is a central particle that is following a parabolic trajectory. So what we can see? Associated to this rod, there is a particle which moves on the same path as if the entire mass of the rod were assumed at that point. This point is known as center of mass, but that is a very crude idea. Let us try to develop the concept of center of mass and its definition. Concept of mass center. Center of mass or mass center of a system of particles is a mathematical point, translational motion of which is the same as that of a particle of mass equal to that of the system under the conditions to which the system is subjected. So that is again, see, very beautiful idea. Actually, center of mass is a mathematical point, or you can say it is not a real material point. It is a calculated point. I cannot say it is a imaginary point. It is a mathematically defined point. What the property of this point is? If we assume a particle of equal to total mass of the system at that point, under the condition or under the forces to which the system is subjected, if the same conditions is applied to the point, the particle will follow the same motion as the system will follow. Actually, what? Translation motion. I'm saying translation motion of system. So what is translation motion of system? Actually, amount of translation motion is total linear momentum. And this idea will help us to develop definition and concept of mass center. Thus, motion of the mass center can be predicted if the conditions to which the system is subjected are known. In the same way as motion of a particle is predicted if the external forces acting on it are known. We will use the same idea to develop the concept of mass center. What is that? Motion of the mass center can be predicted if conditions to which the system is subject are known, in the same way as the motion of a particle is predicted if the external forces acting on it are known. So we'll proceed in the same way and try to lay down the fundamental to analyze dynamics of a system of particle. So what is that? Dynamics of a mass center and Newton's law. Actually, how Newton's law governs motion of mass center. Newton's second law for a system of particles, that is summation Fi vector is equal to summation Mii, that is net sum of all the external forces, that is summation Mii, it is net sum of all effective forces or sum of all mass times acceleration product of all the particles. Here the left hand side represents the net external force on the system and the right hand side the net effective force of the system. Actually, product of mass into A is known as effective force. So that is net external force and that is net effective force of the system. That is what we have earlier explored Newton's second law for a system of particles. Employing the concept of mass center, we can write what is the concept of mass center. If the total mass of the center is assumed at the mass center, or in other words, if at the mass center a particle is assumed, mass of which is equal to total mass of the system, that particle the translation motion of that particle will be the same as translation motion of the system. So summation Fi vector is equal to summation Mii, that is equal to total mass into AC vector. Here M capital denotes the total mass of system. So summation Mi is equal to capital M, and AC is acceleration of mass center. So that is equation. Now we have written it mathematically, but what interpretation it has, let us see. Here M is equal to summation Mi is the total mass of the system, and AC vector is the acceleration of the mass center. If mass of every particle is a constant, we can write what? Summation Fi vector is equal to summation d by dt of Mi Vi vector. And again we can bring this summation sign into the operation of differentiation. So what we get? D by dt of summation Mi Vi. And we can see that is total linear momentum or total amount of translational motion of system. And this is what we can say. Here the right hand term is the time rate of change in total momentum of the system. That right, what is this? Time rate of change in total momentum of the system. Employing the concept of mass center, we can write summation Fi vector is equal to d by dt of summation Mi Vi vector is equal to d by dt of capital M Vc vector. So actually if you solve this, what you get here? M dVc by dt or MAC. So these equations are consistent. So what is that? Here we are told earlier that if a system is subjected to a condition, and if a particle of the mass equal to that of system is placed at the mass center, and this particle is subjected to the same condition, its translation motion will be same as that of the entire system. Here I am saying translation motion means amount of translation motion, and amount of translation motion is linear momentum. Summation Mi Vi is equal to summation MVC. So from here what we can write here, summation Mi Vi is equal to summation MVC. Total linear momentum, that is quantity of translational motion of the system, is equal to momentum of the whole mass due to translation of the mass center. Please here be careful that we are not replacing the system by a particle of equal mass at the mass center. What we are assuming? If at the location of mass center a particle is assumed equal to mass of the system, its motion in terms of momentum will be same as that of the actual system under the same condition or under the same external forces. So that is very remarkable equation. We'll proceed from that equation. Center of mass of a system of discrete particles. A system of several particles of finite masses having finite separations between them is known as system of discrete particles. Discrete means there must be some finite separation between particles. If the separation is infinitely small, we call it continuous mass. So if we want to differentiate a system of discrete particles from a continuous mass, that is the definition of what? A system of several particles of finite masses having finite separations between them is known as a system of discrete particles. Consider a system of n particles of masses m1, m2, mi and mn. At an instant of time, the particles are observed at position vectors r1, r2, ri and rn, moving with velocities v1, v2 and so on, vi and so on and vn respectively. So let us show here actually what concept of mass center represent this idea. Actually here what for better readability of diagram, we are not shown velocity vector of all the particles. Say for ith particle velocity vector is shown and ith particle position vector is shown. If you want to show position vector and velocity vector of all the particles, the diagram will become too much complex to read anything from it. So here now if we add all the terms mi vi for this system, that will be equal to what? a particle at the location of mass center. Suppose here was the mass center, its position vector is RC. So this total momentum will be equal to mvc. So that is what the equation what we had deduced earlier on previous screen. So mvc is equal to summation mi vi. What is that? Total linear momentum means total amount of translational motion of a system is equal to total mass of the system times velocity of the mass center. And this is starting definition or starting equation to develop anything regarding mass center. So what we have, we integrate this mvc dt is equal to summation mi va dt. So this integral is indifferent integral. So if you perform this indifferent integral, what you get? A constant of integration. Summation mrc is equal to summation mi ri plus a constant k vector, and this constant k vector is constant of integration. The above equation relates location of mass center with the configuration of the system. Actually, this information, this summation mi ri includes what? At an instant, position coordinate or position vector of all the particles, and this information is known as mathematically configuration of system. So this equation relates location of position of mass center with the configuration system. But here is a constant term k which is unknown. We have to find its value or its interpretation. The concept of a mass center is used to describe the translational motion of a system. Therefore, the constant of integration k in the above equation can be assumed to be a null vector. Why? Actually, the concept of mass center we are defining to describe motion. So here this equation has no meaning. What meaning is derivative of this equation, first derivative time or second derivative. So once we take derivatives, this k will become 0. So what is, for that purpose, even if we take k0, our results will be same. So for this purpose, we assume the constant integration to be a null vector. So now what we can write? Summation mrc is equal to summation mi ri vector. So this is definition of mass center, how the mass center position vector can be calculated. Location of the mass center can now be expressed by this equation. RC vector is equal to summation mi ri vector upon total mass of the system. In Cartesian coordinates of the system, we can resolve xc, yc and zc. So what is xc? Xc will be summation mi xi upon total mass. Similarly, what is yc? Summation mi yi upon total mass. And what is zc? Summation mi zi upon total mass. Here I explain that ri is the position vector of the ith particle. Similarly, xi is what? X coordinate of the ith particle. What is yi? Y coordinate of the ith particle. What is zi? Z coordinate of the ith particle. So these equation relates x coordinate with all the x coordinates of every particle system. This equation relates y coordinate of mass center with y coordinates of all the particles of system. Similarly, this equation relates z coordinate of the mass center with the z coordinates of all the particles of the system. Now, in this way, we have deduced an equation or enough information to locate where mass center will be for a system of particles. Example 1. Find position of mass center of a system of 3 particles of masses 1 kg, 2 kg and 3 kg located at position vector r1 vector is equal to 4i cap plus 2j cap minus 3k cap, r2 is equal to I cap minus 4j cap plus 2k cap, and r3 is equal to I cap minus 2j cap plus k cap respectively. Here these coordinates are in meters. So what we do? We can use the equation RC vector is equal to summation mi ri vector upon total mass. So RC vector is equal to summation mi ri vector upon total mass. Substituting value, what we get? RC vector is equal to 1 into this position r1 plus 2 kg into this here 2 kg into I cap minus 4j cap plus 2 cap upon total mass and plus 3 kg into this position vector upon total mass. Now we can solve these equations. So what we get? RC vector is equal to 2I cap minus 2j cap plus 2k cap. Now it is not very difficult to resolve. What it will be? That is 4 plus 2 plus 6. So how much for, say, for x, let us verify for x component. 4 plus 2, 6. 6 plus 6, 12. And that is how much? 1 plus 2 plus 3, 6 kg. So 12 by 6, 2. So in this way we can see all the coordinates. So in this way we have developed a method how we can find coordinates or position vector or mass vector of a system of discrete particles if masses of all the particles and position coordinates of all the particles given, or in other words, configuration of system is known. Example 2. 3-point masses 2 kg, 3 kg and 4 kg are lying on the vertices of an equilateral triangle of side L. Find location of the mass center. This diagram is given. What 2 kg is here, 3 kg is here and 4 kg here, and we have to find location of mass center of system. For that purpose we have to assume a coordinate system. So very simple coordinate system will be that consider a coordinate system as shown in the figure. What? We assume this line to be x-axis and this to be y-axis. So here the coordinates of 2 kg are 0, 0. Coordinates of 3 kg what? L, 0. And coordinate of 4 kg is what? Height will be L sine 60. So L root 3 by 2 and this is what? L by 2. So its coordinate will be L by 2, comma L root 3 by 2. Coordinates of the masses are for 2 kg 0, 0. For 3 kg that is L, 0. And 4 kg as I explained here, this will be in midway. So x coordinate is L by 2 and y coordinate this height, that is what? This is L, this angle is 60 because this is an equilateral triangle. So this height will be L sine 60. So L root 3 by 2. So L by 2, comma root 3 by 2L. So these are the coordinates of the masses. Now the task is remaining to find mass center. For this we can use a Cartesian coordinate equation. So xc will be summation mi xi upon total mass. So what it will be? 2 into 0 plus 3 into L plus 4 into L by 2 upon 2 plus 3 plus 4. By solving this, what we get? 5L by 9. Similarly, we can write y coordinate. Yc will be summation mi yi upon total mass. So what is yc? Put the value 2 into 0 plus 3 into 0 plus 4 into root 3 by 2L upon 2 plus 3 plus 4. So what it will be? 3L by 3 root 3. So the coordinates of the mass center are, say, 5L by 9, comma 3L by 3 root 3. So that is a simple procedure how we can calculate mass center of a system of discrete particles. Example 3. Find location of mass center of a system of two particles, masses m1 and m2, separated by a distance r. Actually, this is problem of very peculiar interest. Actually, if you see the collision, there was a very interesting result that perfect elastic collision between two equal masses, velocity exchange will take place. Now, actually, all the examinations are intended to check your application and understanding capability, not your calculation. So whenever in some problem collision will be involved, of course this idea they will involve, so that you can analyze the problem without involving much calculation. Similarly, for mass center, usually two body problems or two particle problems are there, because if you know all about mass center, you can solve it. If you take 3 body, 4 body or n body, only it will increase calculation. So this result is of very great importance. So let us see. If we assume origin at the mass center, vector RC will be a null vector. Actually, what we are doing, we are assuming the origin at the mass center. So position vector mass center will be a null vector. So M1 R1 plus M2 R2 vector will be a null vector because it should be total mass times RC, that is null vector. What it shows? Both of the masses M1 or M2 are positive. Thus, to satisfy the above equation, vectors R1 and R2 must have opposite signs and the mass center C lies somewhere between the two particles on the line joining them, as shown in the figure. Just see interpretation of this equation. What it shows? The R1 and R2 must be oppositely directed and collinear. So initial point of R1, R2 is the mass center and terminal point are M1 and M2. So M1, M2 and mass center are collinear and mass center is somewhere in between the masses. So what are you saying? The mass center of a two particle system lies in between the masses on the line joining them. Say if for general we take M1 here, M2 here. So this vector is R1, this vector is R2 and mass center is assumed to be origin. Substituting magnitudes, we get M1 R1 plus M2 R2 vector is equal to null vector. So we substitute magnitude of R1 and R2. What we get? R1 by R2 is equal to M2 by M1. So what we this M1 R1 plus M2 R2 equal to 0. So here one of the magnitude we have to take with minus sign. So M1 R1 is equal to M2 R2. So R1 by R2 is equal to M2 by M1. So what it shows? Another information that the mass center of a two particle system distance is in the reciprocal ratio of the masses. Actually, that is what? R1 is distance of mass center from M1 and R2 is distance of mass center from M2. So we can say the mass center of two particle system divide the separation between them in the reciprocal ratio of masses and exist on the line between them in between the particles. Knowing that R1 plus R2 is equal to R, we get. So now is the only problem of ratio and proportion. So what R1 will be? Some ratio upon sum of ratio. M2 by M1 plus M2 into R. And R2 will be M1 by M1 plus M2 into R. So R1 is M2 upon M1 plus M2 into R, or R2 is M1R upon M1 plus M2. So that result is very of peculiar interest. So what we can summarize from this problem, mass center of a two particle system lies between the two particles on the line joining them and divides the distance between them in the inverse ratio of masses of the particles. So please remember it, because so many times we have to use or analyze two-body problem, and at the time if you remember it, you can easily locate the mass center of a two-body or two-particle system. Shift of particles and the mass center. Now we come on another interesting idea. If we shift one of the particle, so suppose we have system of n particle and we shift location of some particles, how the mass center will shift? Or if we shift mass center, how the confusion should change? So how these shifts are related? Let us see here. For a system of n particles, relation between displacements of particles of the system and corresponding displacement of the mass center bear the following relation. What? We know total mass into RC vector is equal to summation MIRI. So taking differential, what we take? M into delta RC vector is equal to summation MI delta RI vector. So that is again very simple relation, but it has very important interpretations also. Say example based on that idea. Two particles A and B of masses 10 kg and 30 kg are placed on the x-axis. The particle A is shifted by 7 cm in the positive x direction. By what amount should the particle B be shifted to obtain a shift of 1 cm in the positive x direction in the position of mass center? Actually, just again see, there are two particles A and B. Mass of both are given. A is shifted by 7 centimeter in positive direction. Now we have to calculate by what amount B should be shifted and what amount in what direction, so that there is shift of 1 centimeter in a positive direction of the mass center. So what is given? If you say A and B, so delta RA is 7. Say for X, we take positive direction by positive and this direction negative. So delta RA is 7. Delta RB you have to find, and delta RC is what? Plus 1. So we'll substitute these values. What we have? Summation delta XC is equal to summation MI delta XI. So this vector equation we write in Cartesian coordinate equation. So here we have to take only X shifting. We substitute values. M delta XC is equal to MA delta XA plus MB delta XB from this equation. And now we substitute value. M is total mass 10 plus 30. Substituting the given values, we get what? 10 plus 30 into 1 because it is plus 1. 10 into 7 and it is 30 into delta XB, which we have to find. So from here, delta XB is equal to minus 1 centimeter. So particle B should be shifted in the negative x direction by 1 centimeter. The particle B has to be shifted by 1 centimeter in the negative x direction. Now we proceed on the next idea. Mass center of a composite system of discrete particles. So what we mean by composite system discrete particle? Let us see. A composite system of discrete particles consists of two or more systems of discrete particles. Actually, it is a group of several systems that is called composite system. Consider three systems A, B and C of discrete particles as shown in the figure. See, this is system A, mass M1A, M2A, MIA, MNA. So masses we are denoting by subscript A. So this dash dash encircling was, we are assuming boundary of system. So we call this system A of discrete particles. Now we assume system B. So that is system B. Masses are M1B, M2B, MIB, MNB, and this is boundary of system. And similarly we can assume system C. So that is system C. M1C, M2C, MIC, MNC. Mass centers of these systems A, B and C are CA, CB and CC. So let us locate them. So here mass center of system A. Suppose here is the mass center of system B and here is the mass center of system C. Now what we do? We locate position vectors of these mass centers of the system with respect to an origin, say O. To determine the position vector of the mass center of the composite system, we assume each subsystem to be a particle of mass equal to mass of the subsystem at the location of the mass center of the subsystem. So that is, see here, what we do to find the mass center of this composite system. Composite means that is a combination of all these three systems. What we do? We replace every subsystem by its total mass at the location of its mass center. So here system A will be replaced by the total mass of A at location of CA. System B will be replaced by total mass of B at the location of its mass center CB. Similarly, system C will be replaced by its total mass at this mass center C of C. Now for this we must define where is CA, where is CB, where is CC. For this what I told you, we define this position vector with respect to an origin. Say here is the origin. So what to do? Assuming the position point O to be the origin, position vectors RCA, RCB and RCC of the mass centers CA, CB and CC of the subsystems A, B, C are shown here. See this way. That is a position vector of this CA. That is position vector of CB. That is position vector of CC. Now what we do by using this idea? What is the idea? We replace all the subsystems at their mass centers by their total masses. So here is what? Summation MIA is at this location. Here what summation MIB at this location. Here what summation MIC at this location. So now we can write position vector RC of the composite system consisting of the three subsystems A, B and C is now given by the following equation. What? RC is equal to summation MIA RCA plus summation MIB RCB plus summation MIC RCC upon summation MIA plus summation MIB plus summation MIC. Now again, this equation represents this one. What? This is a particle of mass equal to mass of the system A at the location of mass center of A. Again, same here. That is total mass of the composite system. So in this way, we can find mass center of a composite system of particles. Now example 5. A system of two particles of masses 2 kg and 3 kg has its mass center at -2, -4, -2. And another system of three particles of masses 1.5 kg, 2.5 kg and 1 kg has its mass center at 4, 8, 6. Find the mass center of the composite system of these two given systems. So we follow the strategy. What? This is mass center of system first. So at this point we assume the total mass, what? 5 kg of system, first system. And this is mass center of second system. And we assume at this location total mass of the system, what? 1.5 kg plus 2.5 kg plus 1 kg. And in this way we locate the mass center of the composite system. So here position vectors RC of a composite system consisting of the two subsystems A and B is given by the equation. What? RC is equal to summation MIA RCA plus summation MIB RCB upon summation MIA plus summation MIB. So it is well explanatory. What? At this location we are assuming the entire mass of system A. At the mass center of B we are assuming the entire mass of system B. So now the task is remaining to substitute the values. Substituting the given values, we get RC is equal to 2 plus 3 and what? -2i cap minus 4j cap minus 2 cap plus 1.5 plus 2.5 plus 1 into 4i cap plus 8j cap plus 6k cap upon 2 plus 3 and plus 1.5 plus 2.5 plus 1. This is here and this is here. Now we calculate it. And what we obtained, RC is equal to I cap plus 2j cap plus 2k cap. And I'm leaving the calculation to you. So in this way, we can find mass center of a composite system. What is composite system? It is a group of several systems. Mass center of a continuous distribution of mass. Actually, till so far we are discussing about how to locate a mass center of discrete particle system. And what is discrete particle system? In discrete particle system, several point masses are separated by finite distances. Now, if these all finite distances are become vanishingly small, this system will become a continuous mass distribution. Now, we are here to locate how to calculate mass center of a continuous mass distribution. Why it is of great importance? Actually, all the bodies what we face in day-to-day life are extended bodies having continuously filled with mass. So all of them are continuous mass distribution. So this idea is going to be more useful. A continuous mass distribution is a collection of infinitely large number of point masses with vanishingly small separations between them or between any two adjacent point masses. All material objects used in day-to-day use are examples of continuous mass distribution. So that's why this idea what we are going to discuss is going to be very much important. So now we proceed. Consider an infinitely small portion of mass dm of a continuous mass distribution as shown in the figure. Position vector of the mass center of such a body is given by the following equation. Actually, here is this diagram. We are assuming this is continuous mass distribution. In this continuous mass distribution, here we are assuming an infinitely small point mass of mass dm, part mass dm, and its position vector is r vector. Now suppose position mass center is here and its position vector is given by rc. So how we can write rc? With the idea of discrete particles. So what? Summation miri upon total mass. So here what? We have to add infinitely large number of summation miri which are having infinitely small differences. So it is area of integration. So what we do? rc is equal to integral r dm upon integral dm, and this limit extend over the entire mass distribution. So it may be in terms of volume, or it may be in terms of a line, it may be in terms of a surface if it is a plate. If it were a rod, it will be in terms of length. If it is a volume, it will be in terms of volume. So I'm not writing here limits. So please take care. It is always a definite integral extending the entire mass distribution. In terms of Cartesian coordinates, what we write? Say here, coordinate of dm are x, y, z, and coordinates of mass center are x, c, y, c, z, c. So xc will be x dm upon integral dm. So xc will be integral x dm upon integral dm. Similarly, what will be yc? Integral y dm upon integral dm. What will be zc? Integral z dm upon integral dm. Now we are equipped with the idea how to locate mass center of continuous mass distribution or bodies, or kind of bodies which we face in day-to-day use. Mass center of uniform symmetrical bodies. Before we proceed of employing those formula what we develop into calculation, let us try to find some ways how we can simplify our calculation in some instances. So for purpose, we take a mass center of uniform symmetrical bodies. So what we mean by symmetrical bodies? By the term uniform, it is obvious its mass density at every point is the same. Mass density does not vary from point to point is the meaning of uniform. But what is meaning of symmetric? Let us define it. A symmetric body has one or more axes of symmetries, AOS. And what is axis symmetry? An axis of symmetry is a mathematical line flipping of the body through 180 degree about it does not alters the configuration of system. So what is that? A body is said to be symmetric if you can find a line, mathematical line. If the body is flipped by 180 degree about that line, the configuration appear as it was before flipping. It means configuration or appearance must not change. So such a body is called symmetrical body, and such a mathematical line is called axis symmetry. We call it AOS. Symmetry of a uniform body suggests that the following conclusions. What the conclusions are? First, mass center of uniform symmetrical bodies lies on the axis of symmetry. We'll explain why it is so, but let us first take it granted intuitively. That is, mass center of uniform symmetric bodies must lie on its axis of symmetry. If a symmetric body has more than one concurrent lines of symmetry, the mass center lie at the point of concurrency. What? If a body has more than one AOS and both the AOS are concurrent, the mass center will be at the point of concurrency. Actually, after some time, you'll find that these concepts are very intuitive, but we'll try to lay down the fundamental behind them. We'll try to develop these concepts. Though the above conclusions are very intuitive, yet they can be well explained with the help of the fact that mass center of a system of two identical particles lies at the midpoint on the lining joining them. Here we are again using what idea? Mass center of a two-particle system. What we have seen? That mass center of a two-particle system divides separation between them in the reciprocal ratio of masses and lies on the line joining them. So if the masses are equal, so mass center will divide the separation between them in equal parts. So in this way, what is written here? That mass center of a system of two identical particles lies at the midpoint on the line joining them. using this idea, we try to explain these intuitive facts. Say here, this idea is explained here. This mass M, this mass M, it is two particle system. So mass center will be at equidistance. So separation between particles is R. So mass center will be R by 2 from here and R by 2 from here. A symmetric uniform body can assumed consisting infinitely large number of such symmetric pairs. Mass center of body must lie on the common axis of the symmetry of all such pairs. Actually, this idea is again not very difficult. Any symmetrical body can be assumed consisting of infinitely large number of such pairs. And if all these such pairs, mass center lies on a line, common line, that common line will be axis symmetry, and mass center must lie on the axis symmetry. Let us see with the particular examples. Mass center of a straight uniform rod. So you can see, consider two identical infinitely small parts A and B at equal distances from the center C of the rod. Mass center of the parts is the C. Say here, this rod. And you can see this middle line, a line perpendicular rod passing through its center is the AOS. Because if you flip the rod by 180 degree about this line, the rod will appear the same because it is uniform rod. Now assume this part A of DM and DM here C. Mass center of these two parts will be C here. The whole rod can be assumed to be made of large number of such systems, each having its mass center at the midpoint C of the rod. Therefore, mass center of the whole rod must be at its midpoint that lies on the axis symmetry. So the idea what we have done here, we have explained here for a straight rod. Now we extend the idea for a curved rod, symmetric curved rod. Mass center of a uniform symmetric curved rod. Consider a curved uniform symmetric rod as shown in the figure. Say here. The mass center of a pair of two identical infinitely small parts A and B being equidistant from them must lie on the AOS. How? Say we have this rod, we have mass center of a pair of two identical infinitely small parts A and B being equidistant from them. Actually what if we assume two pairs like that, say A and B, mass center of these two pairs will be equidistant from them, so it will be here. Similarly, we can say another part, this and this, the mass center will be here. For this and this, mass center will be here. So for all such parts, mass center will be on that line. So the mass center rod must be on that line, and this line will be axis symmetry. So how we defined axis symmetry earlier? One way. Axis symmetry is a mathematical line. If the body is flipped about it through 180 degree, configuration should not change. Or in other words, if we can assume large number of symmetric pairs, and if mass centers of all the symmetric pairs exist on a common line, that common line will be the axis symmetry. But earlier idea was more intuitive to understand because it involves geometry. So here what we have, this rod can be assumed consisting of infinitely large number of such particles or pairs. The mass center of rod must lie on the AOS. Actually, for this pair, mass center is here, and this rod can be assumed for consist of infinitely large number of such pairs. For another pair here, mass center will be here. For this pair, mass center will be here. So for all pairs, mass center will be on the line. So the mass center of the entire rod must be on the line. Now we extend the idea to a uniform symmetrical lamina. Lamina means a plane surface of very thin plate of arbitrary shape. Mass center of a uniform symmetric lamina. So it assumes symmetrical lamina. The symmetric uniform lamina can be assumed consisting of a large number of thin uniform parallel rods like AB shown in the figure. So this is what a lamina, it is symmetrical about this line, so we call AOS. This lamina can be assumed consider large number of uniform parallel rods. So this way. Every rod has mass center here. So if you assume a rod here, mass center will be here. If you assume a rod here, mass center will be here. So mass center of all the rods are on the AOS. So mass center of the entire lamina must be on the AOS. All these rods have mass center on the AOS. Therefore, the whole lamina has its mass center on the AOS axis of symmetry. Now we have extended the idea of symmetry from two particle system, two identical particle, to a uniform straight rod, then a uniform curved rod, then a uniform symmetric lamina, and now we extend the idea to a uniform three-dimensional continuous distribution of mass. A three-dimensional continuous distribution mass is called a solid object. Here the term solid does not represent state of matter. Solid means three-dimensional. Mass center of a uniform symmetric solid object. Consider a uniform symmetric solid object. It can be assumed composed of a large number of thin uniform parallel plates shown in the figure. Say here, this three-dimensional. Actually, how it is assumed, that is this lamina is rotated about AS through 360 degrees. So what volume it sweep? It is the solid volume. Now here we can assume a disc or plate. Actually, if it is symmetrical, so it will be circular. Now what we have? It can be assumed composed of a large number of thin uniform parallel plates shown in the figure. See, for every such disc, mass center will be here. So for this disc, mass center will be here. So for every disc, mass center lie on the AS. So the mass center of the solid object lies on the AS. All of these plates have mass centers on the AOS. Therefore, the solid object has mass center on the AOS. So in this way, we have extended the idea what? If a uniform body has axis symmetry, mass center must lie on the axis symmetry. And if a uniform object has more than one concurrent axis symmetries, mass center must be the point of concurrency. So these ideas will simplify our calculation greatly. So sometimes or every time we should be ready to use or to take advantage of these symmetry consideration. Mass center of a uniform object. Again from here, that is an intuitive fact. For a uniform object, following the similar reasoning, it can be shown that the mass center of a uniform bodies lies on their centroids, that is geometrical center. That's again an intuitive idea. If a body is uniform, its mass center lie on its geometrical center, or that is called centroid. Say for sphere, mass center will be its center, uniform sphere. Say if you call a square plate, uniform square plate, mass center will be its midpoint. Similarly for rod, so that is what mass center of uniform bodies will lie at their centroid. So if we are given a uniform body and we know its centroid location, so mass center will be at the centroid. Now what I told you, that we must be ready to take advantage of these ideas. We take the example 6, mass center of a segment of uniform circular rod arc. So first we take a uniform circular arc and we want to calculate where its mass center will be. So that is description of the arc. Find location of mass center of a thin uniform rod bent into shape of an arc of radius r, subtending an angle theta at the center. So that is situation. That is thin. Actually, this diagram is shown thick, but it is thin. So radius is r and it subtend an angle theta at the center. We have to locate mass center of this arc. Now what we can think? I have suggested you be ready to exploit the advantage of symmetry idea. Now here you can think the angle bisector is AOS, because if you flip the arc by 180 degree about the angle bisector, it will appear the same as it is. So mass center must lie on the angle bisector. Now knowing this idea, if the angle bisector assume the x-axis and here will be y-axis and z-axis, so mass center is on the AOS or on the x-axis, so y and z coordinates of the mass center will be 0. So there is no need to calculate y and z coordinate. So that is simplicity what we can extract from the symmetry consideration. So how we proceed? The angle bisector of the arc is the AOS. Thus, the mass center must lie on it. If we assume the angle bisector as one of the coordinate axis, say x axis, y coordinate of the mass center becomes 0. So let us proceed how. If you assume here x-axis, the mass center of the entire rod must be somewhere on the x-axis. So its y coordinate will be 0. So we have saved our time from calculating another coordinate. For this, let us divide this by a small part dm, because how we can find mass center of continuous mass distribution? Integral r dm upon total mass, or in x coordinate integral x dm upon total mass. Dm is what? A small, infinitely small part of the mass distribution. So you assume here a, infinitely small part, that extend from angle alpha to alpha plus d alpha. So this angle is d alpha, infinitely small. And its x coordinate is what? R cos alpha. Because it is a point, so you can say x coordinate of this part is r cos alpha. Consider an infinitely small part A, x coordinate of which x is equal to r cos alpha, and mass is dm. Dm is what? Lambda r d alpha, where lambda is the line mass density. What is line mass density? That is, if body is uniform, it will be m by total length. So x coordinate, this, what is mass? Line mass density into length. So lambda and length is what? R d alpha. So that is dm. So we have written dm and x. Now we can substitute this value in the relation. X is what? Integral x dm, extending over the entire mass distribution, upon integral dm, extending again over the entire mass distribution. So x is equal to integral x dm upon integral dm. Of course, these are different integral, but we are not showing the limits. So what we have? Now we put the limit. So minus theta by 2 plus theta, r cos alpha and r alpha d alpha. Again from minus theta by 2 to theta by 2, and this. So what is here? X and dm is defined in terms of alpha. So limit of alpha is what? From this. Here it will be minus theta by 2. Here it will be plus theta by 2. So limits are from minus theta by 2 plus theta by 2. For x we have written what? R cos alpha. For dm we have written what? Lambda r d alpha. Again for dm what we written? Lambda r d alpha. Now let us simplify here. So you can see lambda and r are constant. So we can take outside of integration. So lambda and r square come out, and here lambda r will come out. So after cancellation, what is remaining? R in the numerator. So on inside what we integrate? Cos alpha d alpha from minus theta by 2 theta by 2. Again what we indicate here? D alpha from minus theta by 2 to theta by 2. So xc will be r minus theta by 2 to theta by 2 cos alpha d alpha upon integral minus theta by 2 to theta by 2 d alpha. Now let us say evaluate this one. So this integral will be alpha from minus theta by 2 theta by 2. So what do you get? Theta. So denominator is theta. And what we have here? Sine alpha over this limit. So sine theta by 2 minus sine of minus sine theta by 2. So what you get? 2 sine theta by 2. And that theta we bring in denominator. So here what we have? Theta and upon 2. So theta by 2. So what do we get now? X is equal to r sine theta by 2 upon theta by 2. So that is a very symmetrical formula. So for an arc, what is mass center? R into sine of half angle upon half angle. So theta by 2 is half angle. So again, I'm reiterating the x distance of mass center from the center is what? R into sine of half angle upon half angle. And here this half angle must be used in radians. Now let us make use of the formula. Actually, that previous problem can be remembered as a standard formula. Find coordinate of the mass center of a uniform quarter ring of radius r shown in the figure. So that is quarter ring. Quarter means it extends angle pi by 2 at the center. So how we can find coordinates of the mass center? What the idea is, mass center of a segment of a uniform circular rod of radius r and angular span theta lies on its angle bisector at a distance rc from the center given by the equation. That is what result of previous problem. What? Mass center of a segment of uniform circular rod, that is arc of radius r and angular span theta, means the arc subtending angle theta, means up to what angle the arc is spread, lies on its angle bisector at a distance rc from the center given by equation what? Rc is equal to r sine theta by 2 upon theta by 2. So that formula we will use here. Now the entire theta is 90, so theta by 2 is pi by 4. Making use of the above fact, distance OC of the mass center of the given quarter arc is, say in this diagram, that is angle bisector. So half angle is pi by 4, here again pi by 4. Suppose here is the mass center C. So this RC is OC. So OC will be what? R into sine pi by 4 upon pi by 4. So R sine pi by 4 upon pi by 4. So sine pi by 4 is 1 by root 2. So what we get here? 2 root 2 R upon pi. So that is OC. Now what is remaining? We have to resolve OC into its component, OC vector, or you can find coordinates of this. So XC will be what? OC cos pi by 4. What is YC? OC cos pi by 4 if you take this pi by 4. So from the geometry of the setup, what we have? XC is OC into cos pi by 4. So that is 2R by pi. Similarly, how we can find YC? YC is what? OC into sine pi by 4. Here we are taking this pi by 4. So that this again 2R by pi. So now we can write coordinates of the mass center. So coordinates of the mass center XC, YC are what? 2R by pi, comma 2R by pi. So we have made use of this relation. Let us see one more example how this relation can be used. Now we try to find mass center of a semicircular arc. Example 8. Find coordinates of the mass center of a uniform semicircular ring of radius r shown in the figure. So that is this. Its radius is given to be r, and we'll proceed in the same way. Mass center of a segment of a uniform circular rod arc of angular span theta lies on the angle bisector of the arc at a distance from the center given by the equation. What RC is? R sine theta by 2 upon theta by 2, means R sine of half angle upon half angle. So here half angle is pi by 2. And again we can see by symmetry this y-axis is the angle bisector. So center mass must be on the y-axis. So x coordinate is 0. Making use of the above fact, distance OC of the mass center of the given semicircular arc rod is, see in this diagram, here is the C. So OC is what? R sine this half angle pi by 2 upon pi by 2. So for theta, that is pi. So it is pi by 2. So what you get from geometry of the setup, OC is equal to R sine pi by 2 upon pi by 2. So this will be equal to 2R upon pi. So that is OC. And this is the location of mass center. Y coordinate, x coordinate is 0. So coordinates of the mass center XC, YC are 0, 2R by pi. Now this idea we have used how to locate mass center of an arc. Now we extend the idea how to locate mass center of a sector of a circle. Example 9. Mass center of a sector of a uniform circular lamina. Find location of mass center of a sector of a uniform circular lamina of radius r subtending an angle theta at the center. Say in this way. That is, now this is lamina, its sector of angle theta, radius is r. Again, we can see this angle bisector is AOS, so mass center will be on the AOS. Now, if we assume it x-axis and it is y-axis, so mass center y coordinate will be 0. It will have only x coordinate. So let us see how we proceed here. The angle bisector of the sector is the AOS. Thus, mass center must lie on the angle bisector or in it. The sector can be assumed consisting of infinitely large number of infinitely thin circular arcs. One of such arc of radius L and width dl is shown in the figure, say here. Now, instead of taking a small part, let us take this one. Because location of mass center of this is known. Say mass center of this arc is here at x. And x is what, this distance? So x is what? L sine half angle upon half angle from the idea of mass center of an arc. So denoting mass of this arc by dm and distance of its mass center from the origin by x. Distance of mass center of the sector from the origin is given by what? X is equal to x dm upon integral dm. Now we have to find what is dm and what is x. X we have seen what is r sine theta by 2 upon theta by 2. Instead of r we take L, denoting surface mass density of the lamina by sigma. Mass dm of the circular arc shown is given by dm is equal to r L theta dl. What is L theta dl? Area, this shaded area. The length is L theta and width is dl. So what is area? L dl. So sigma into area, that is what we can write here, L theta, sigma theta L dl. Sigma and theta are constants, we are taking at one side, and L dl are variables, so we are doing this. So we have obtained expression for dm. Now we have to write what is x. Distance x of the mass center of the arc from the origin is given by x is equal to L sine theta by 2 upon theta by 2. Now we substitute these values of dm and x from 2 and 3 equation to equation 1, and performing integration we can find the x coordinate of this mass center. We write the equation for reference. X is equal to x dm upon integral dm. Equation 1. Dm is equal to sigma L theta dl or sigma theta L dl. Equation number 2. And x is equal to L sine theta by 2 upon theta by 2. That is equation number 3. What we do? Substituting expressions for dm from equation 2 and that of x from equation 3 in equation 1 and extending the definite integral over the limits from L is equal to 0 to L is equal to R, we obtain the location of mass center of the sector. Actually, if you vary L from 0 to R, the entire sector will be covered. So x will be from 0 to R, L sine theta by 2 upon theta by 2, that we are writing for x, and for dm what to write here? Sigma theta L theta, and again 0 to R, sigma theta L theta. Now what we can take outside? Sine theta by 2 is constant, theta by 2 is constant, sigma is constant, theta is constant. So all we take outside, and after performing calculation what we get? 2 by 3 r sine theta by 2 upon theta by 2. So how to evaluate this integration and how to calculate this algebraic expressions I am leaving for you. So that is coordinates of the mass center of a sector. And now it is very easy to remember. For arc it is r sine half angle upon half angle, and for sector that expression is multiplied by 2 by 3. So that is what coordinate of a sector of a circle. Now we make use of this formula because sometimes you have to use it as a standard result. Example 10. Find coordinates of the mass center of a uniform quarter sector of a circular lamina of radius r shown in the figure. This The parallel example we have taken, the similar example we have taken for the arc. Now we are taking same example for sector. So how we proceed? Mass center of a sector of uniform circular lamina of angular span theta and radius L lies on its angle bisector at a distance RC from the center given by the equation. Now we write the equation. Just you can, by a little bit of addition, you can remember. Just remember the distance of mass center for arc, that is r sine theta by 2 upon theta by 2. And that expression is multiplied by 2 by 3. It will become expression for a sector. So what is RC? 2 by 3 r sine theta by 2 upon theta by 2. So now how we proceed? Making use of the above fact, distance OC of the mass center of the given quarter sector is in this way. It will be on angle bisector. So here, so OC is given by this. So how we calculate OC? OC is 2 by 3 r sine pi by 4 upon pi by 4. So it will be 4 root 2 r by 3 pi. Now we have to make x and y coordinate, xc and yc. So from the geometry of setup, what we write here? X is OC cos pi by 4. X is OC cos pi by 4. So cos pi by 4 is 1 by root 2. So this root 2 will cancel. So what you get? 4r by 3 pi. The similar value will be 4yc because this angle is pi by 4. So xc and yc will be equal. So yc is OC sine pi by 4. So it is again 4r by 3 pi. Now we can write the coordinates. Coordinates of the mass center, xc, yc are 4r by 3 pi, comma 4r by 3 pi. Now we take again parallel example. We find mass center of a semicircular plate. Example 11. Find coordinates of the mass center of a uniform semicircular lamina of radius r shown in the figure. That is, again by symmetry, you can see the mass center will be on the y-axis because y-axis is the axis symmetry. And by using angle bisector formula, we can find the mass center. So we write that is mass center of a sector formula. So I'm again reproducing the result. Mass center of a sector of a uniform circular lamina of angular span theta and radius r lies on its angular bisector or angle bisector at a distance RC from the center given by the equation. RC is equal to 2 by 3 into that of r, r sine theta by 2 upon theta by 2. So 2 by 3 r sine theta by 2 upon theta by 2. Making use of the above fact, distance OC of the mass center of the given semicircular lamina is, now let us again here, mass center is here. So you can see x coordinate 0, we have to find only this OC, this RC will be the y coordinate. From the geometry of the setup, OC is equal to 2 by 3 r sine pi by 4 upon pi by 4. So what we get? 4r by 3 pi. So coordinates are 0, 4r by 3 pi. So 0, 4r by 3 pi. So in this way, we have seen how we can find mass center of some continuous mass distributions. Now let's come on example 11. What is that? Find coordinates of mass center of a non-uniform rod of length L. Line mass density lambda of which varies as lambda is equal to ax plus b, where x is a distance from an end of the rod and a and b are positive constants. How we proceed? Here we are talking about variable density. This rod is not uniform, it is non-uniform. So again we take the same part procedure. We assume an infinitely small part of the rod. We find dm for that. We find distance of that x. So x dm upon integral dm will be the location of mass center. Assume the rod to be lying on the x-axis with its lighter end on the origin to make mass distribution equation consistent with the coordinates. system. Actually, lambda increases with x, so at here lambda increases with x. So if we keep lighter end at the origin, so this equation will be consistent. So in this way, the rod extends from x equal to 0 to x equal to L, and lambda is ax plus b. The rod can be assumed consisting of infinitely large number of infinitely small parts, each of mass dm, extending from x to x plus dx. So this dm extend from x to this point is x plus dx. So dm will be lambda dx, and we have to substitute value of lambda given from here. And now what we use, mass center of the rod is given by the following equation, extending the integration over the limits from x equal to 0 to x equal to L. So xc is equal to x dm upon dm, that is the formula. Now for this rod, xc will be 0 to L, x dm upon 0 to L dm. Now for dm we substitute lambda dx. So xc will be x into lambda dx upon 0 to L lambda dx. Now lambda and lambda we cannot cancel because they are variable. So we substitute value of lambda. X ax plus b dx upon integral ax plus b dx, and numerator and denominator we can calculate separately, and after that what we find, x is equal to 2al plus 3b into L upon 3al plus 2b. So that is distance of mass center of the rod from the origin. Now we can discuss another important idea, that is mass center of composite system of several bodies. Bodies means continuous mass distribution. Composite system of several bodies means it is group of several solid objects. It is group of several rigid bodies or solid objects. Consider a composite system of 3 bodies of masses m1, m2 and m3 as shown in the figure. Mass centers C1, C2 and C3 of the bodies are located by position vectors RC1, RC2 and RC3 relative to the origin O of a coordinate system. Now just see, the first body M1, its mass center is here. Second body of mass M2, mass center is here. Third body mass M3, mass center is here. And suppose here is the origin, and this is position vector of the mass center of first body. RC2, this is position vector of mass center of second body, and RC3, position vector of mass center of the third body. Now what we do, as we have done in composite system of discrete particle, the same approach we here. We replace each of the body by its mass on its mass center. To determine the position vector of the mass center of the composite system, we assume each constituent body to be a particle of mass equal to that of the constituent body at the location of the mass center of the constituent body. So this statement seems to be somewhat twisted, but to make the meaning specific, we have to write such language. Now in common language, what we can say, we replace each of the bodies by their mass on their mass center, and in this way we have 3 system of mathematical particle, and now we can find mass center. So position vector RC of the mass center of the composite system is now given by the following equation. What? RC will be M1 RC1 plus M2 RC2 plus M3 RC3 upon M1 plus M2 plus M3. So M1 RC1 plus M2 RC2 plus M3 RC3 upon M1 plus M2 plus M3. For a composite system of n bodies, we can extend it. RC is equal to summation I is equal to 1 to n mi RCI upon summation I is equal to 1 to n mi. That is, now it is not need to write such cumbersome, just write simply summation and the meaning will become conveyed. So what? Summation mi RCI upon summation mi. So in this way we can find mass center of system of several bodies or composite system. Let us find its applications. Say example 12. Two rods, each of mass m and length L, are placed along the coordinate axis. Find mass center of the system. So how this? One rod is placed along the y-axis, other rod is placed along the x-axis. So how we can find the mass center? We replace each of the rods by its mass, a particle by equal to its mass at the location of the mass center of the rod. So what we say, the mass center of this rod will be here L by 2 and here it will be L by 2. So we assume a particle of mass m at L by 2 here and particle of mass m L by 2 here. Both rods are assumed to be replaced by particles of masses equal to the respective rods located at the mass centers of the respective rods. So what we do, here m is replaced here L by 2 comma 0 and m is here 0 comma L by 2. Now we have a system of discrete particles. So coordinates of the mass center of the composite system is now given by x is equal to summation mi ri or summation mi, and in terms of xc, the coordinate what? Summation mi xci upon summation mi. And what is yc? It will be summation mi yci upon summation mi. So we substitute the values, m into L by 2 plus m into 0 upon m plus n. So what it will be? L by 4. Similarly for yc, summation mi yci upon summation mi. Now we substitute the values. What yc is equal to m into 0 for this rod and for this m into L by 2 upon m plus n. Again we get L by 4. So the coordinates of the mass center are L by 4 comma L by 4. Now see, here when we are studying mass center of discrete particle system, it appears that that article we are developing just to make some problem and solve them. But here you can see use of that. Actually, how to locate mass center of discrete particle system is a basic building block in calculation of mass center. And the idea can be used in this way to find mass center of realistic objects. Example 13. Find mass center of the following composite body made by joining a uniform disk of radius r and a uniform square plate of the same mass per unit area. So surface mass density of both the objects are same, and this is set up. And that is a disk and here the plate. So length and width of the plate are 2r and mass density are same. So what we do, we know that location of mass center of disk is here at the center of disk. So it will what at distance r. So coordinate are what? R comma 0. And location of mass center of square plate is here. So that is r, r and again r. So it is 3r. So coordinates are 3r comma 0. Now coordinates of mass center of these two bodies we can find very easily. The only task is remaining to write their masses. And the masses we write in terms of surface mass density, assuming it to be sigma. To determine the mass center of a composite system of bodies, the constituent bodies are assumed to be particles of masses equal to corresponding bodies located on their respective mass centers. Since the constituent bodies are uniform, their mass centers will be at their centroids. So mass center of the disk, it will be r comma 0. Mass center of the square plate, it will be r, r and r. It will be 3r comma 0. Now we write masses. Now we have to write expression for masses of the bodies denoting surface mass density for both of them to be sigma, because it is given. Mass of the disk, what? Sigma into area pi r square. So m1 is sigma into pi r square. So we can write sigma pi r square. Mass of the square plate m2 a sigma into 2r square, that is area of the square plate. So it is 4 sigma r square. Now we substitute these values in the expression. What is xc? Xc is summation mi xci upon summation mi. Coordinates of the mass center of the composite system is now given by x is summation mi xci upon summation mi. So we put the values. Xc is equal to sigma pi r square for disk and into r into 4 sigma r square into 3r upon, that is pi r square upon 4 sigma r square. This. Now by solving, what we get? R pi plus 12 upon pi plus 4. How? So we can see, we can verify it. I am leaving the verification for you. What is YCI? Summation mi into YCI upon summation mi. Now you substitute the values. What is YC? Is 0. Why? This x-axis is axis symmetry. So mass center must be on the x-axis of the composite body. So y coordinate must be 0. So no need to substitute values in it and getting 0. Now if you put the values, and because both terms will be multiplied by 0 and 0, so we'll get 0. Coordinates of the mass center, that is, we can write here r pi plus 12 upon pi plus 4 comma 0. So that is an idea of how we can find mass center of composite bodies. Mass center of truncated bodies. Sometimes we have a body, some portion of it is removed. How we can find mass center of that? For that we take idea of the composite body. That is how a truncated body is obtained by removing a portion from a body. So that is called truncated body. If we add the removed portion in the same place, we obtain the original body. That is the idea what we use. This idea combined with method used for composite system can be used to find mass center of a truncated body. Actually, that is a very beautiful idea. And how it will be implemented, let us see. We understand it by an example. We take very simple example. 1/4 portion of a uniform square plate is removed as shown. Find mass center of the remaining portion. So that is a portion plate is given, and this 1/4 portion is removed. Now what is that? If you place the removed portion here, we find the entire plate. And what is beauty? The mass center of entire plate is known. Mass center of this removed portion is known. And this has to be found, and this we can find from the idea of composite body. So how we solve? That is, we use the idea, that is the truncated body. Let us is mass center CT for truncated XT YT. Plus we place the removed portion at its place. So here. So its mass center will be what? 3a by 4 and 3 by 4. How? That is, this is what? A by 2. And what? Again a by 4. So 3a by 4. So similarly, this is b by 2. So this is what? B by 4. So total distance is b by 4. So mass center of removed portion is 3a by 4 and 3b by 4. So if you add these, what you get? The original plate. And its mass center will be a by 2 and b by 2. Now we use the idea of composite body, and we see only these two things are unknown in the equation. We get one equation for x, so in which only xt is unknown. So we can find xt. We get another equation for y coordinate in which yt will be unknown, so we can find yt. So that is a very simple idea. Let us proceed how we do it. Denoting masses of the original body or mass of the original body by m. If we denote its mass to be m, its mass will be m by 4, its mass will be 3m by 4. So mt xt plus mr xr is equal to m naught x naught. So 3 by 4m into xt plus m by 4 into xr means 3a by 4 is equal to ma by 2. Now by solving this, what we get? Xt is equal to 5 by 12a. Similar thing we can do for the y coordinate. So what? Mt yt plus mr yr is equal to m naught y naught. M naught is m. This is m by 4. It is 3m by 4. Yr is this 3b by 4, and y naught is b by 2. Let us substitute values. So here, that is similar equation, only see here, A is replaced by B. So here, just see, and xt is replaced by yt, so we'll get the same answer. So here, please write it, read it yt. So yt is 5 by 12b. Mass center of the given truncated body is 5 by 12a, 5 by 12b. Of course, in some of the textbooks, to find mass center of such body, concept of negative mass is introduced. What? We assume here a body of negative mass and use the same equation. But I personally feel, why should we use an idea which is not existing? And if you can find solution in the similar way by using realistic ideas, actually assuming negative mass may create sometimes some conceptual difficulty, because from negative mass, using same laws of physics, we can find very surprising result. Suppose we have two masses. If both are positive, they will attract by gravitational acceleration. So if released, they will rush up towards each other. Now see, if we take two negative masses, they will again attract each other. But when released, what will happen? They will move apart. Why? Because from Newton's law, acceleration is F by m. So F is towards each other. Upon negative mass, acceleration will be outside. So by using such ideas, we may commit some kind of conceptual mistakes at some places. So what I recommend, as far as possible, try to use realistic ideas. So example 15, we take another example of the same type. Find mass center of the following truncated disk made by removing a disk of radius equal to half of the original disk as shown in the figure. Radius of the original uniform disk is r. So here is the disk. Here this portion has been removed, so we obtain a truncated bodies, denoting mass per unit area of the original body by sigma. So it will be mass per unit area for all the bodies. We can express masses mt, mr and m0 as shown. So m0 will be sigma pi r square, mr will be sigma pi r square by 4. Why? Because its radius will be r by 2, so area will be pi r square by 4. So it will be m0 by 4. What will be mt? This minus that, so it will be m0 minus m0 by 4, so 3 m0 by 4. So masses are in ratio what? m0, m0 by 4 and 3 m0 by 4. So we use these values. Mass center of the removed and original bodies are, for original bodies, for removed body it will be r by 2 xr, and x original will be 0 because the original body means it is before truncation, so 0. So its mass center will be here. So we use the idea, if the removed portion is placed at its place, we get the original body from the truncated bodies obtained. So plus, if you superimpose this, what we get? This. Now what the idea is, mt xt plus mrxr is equal to m0 x0 for x coordinate, because you know all the bodies have x axis at axisymmetry, so y coordinates of all the bodies will be 0. So mt xt plus mrxr is equal to m0 x0. Let us substitute the values. For mt, what is 3m0 by 4? What is xt? That we have to find. What is mr? m0 by 4. And so coordinate is r by 2. So m0 into 0 its coordinate. Now in this equation we see only xt is unknown, m0 will cancel out. So by solving, what we get? Xt is equal to minus 1 by 6r. So mass center of this truncated body is here at minus 1 by 6r. Due to symmetry, yt is 0 because x-axis is AOS. Mass center of the given truncated body, that is minus r by 6 comma r. Now it is time to conclude today. Today we have discussed what is mass center, where it will be used. Please keep in mind, mass center will be used to predict translation motion of a system of particles. Only translation motion. And for this purpose, we must know how to locate mass center. In today's lecture, we have seen various methods how to locate mass centers of various systems or various bodies. And in the next class, we'll discuss about how to use the idea of mass center in describing translation motion of bodies or system of particles. Till then, thanks for patient listening. We'll meet in the next class. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thoughts. The physical entities which seems to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.